Extreme physics.
All right, let's take a look at some Newton's second law problems. This is going to be the heart of this course. It's important in these Newton's second law problems that we stay organized, because very soon they're going to get really big. And if we're not organized, it's going to get really convoluted. So we need to have a process involved. And as long as we do that, then even if we have like a series of 7 equations and 7 unknowns, it's pretty manageable. On the other hand, if you just randomly calculate things and don't have a plan, it can get out of hand quickly. So let's take a look at, we have a traffic light problem. This is a statics problem. So we have a traffic light. First thing we always want to do is draw a picture. Here I have the traffic light. I'm going to circle the object of interest, which is the traffic light. And that allows me to see what the contact forces are. To get an accurate free body diagram, make sure we have an accurate free body diagram. Otherwise, things go to hell really fast. The mass of this thing they gave us was 5 kilograms. It doesn't seem like much mass for a traffic light. I think it's a dubious problem. But anyways, it's 5 kilograms. We have a cable holding it at 60 degrees and 30, like that. And that seems odd too. But anyway, that's what we have. First thing we're going to do is draw a free body diagram.
Pause the video now.
Set up a coordinate system. Like that. And let's see what we have here. We have 60 degrees. We have a tension force. And I'll call that T2. And over here, we have another tension force, which I will call T1. 30 degrees like that. Okay, that's in contact. Those are the only things in contact. So let's see, any forces at a distance? Oh yeah, there's gravity. Force of gravity, straight down, like that. All right, there's our free body diagram. This one's pretty straightforward. They won't always be this much. Next thing we want to do is we want to state the physics. We're going to apply Newton's second law. The vector sum of the forces equal mass times acceleration. All right. But we don't really want to deal with the vector nature of this. We're going to break this into horizontal and vertical components. And what that's going to allow us to do is replace a vector operation with scalar operations, where we're just adding and subtracting numbers. That makes it a lot easier than adding vectors. So we're going to say, all right, now this is where we need to stay organized. In fact, I'm going to move this. I don't like it there. Let's give ourselves some room to breathe. We're going to state the physics here. Sum of the forces, the vector sum of the forces equals mass times acceleration. But that also means that the sum of the forces in the x direction equal mass times acceleration in the x, and sum of the forces in the y equal mass times acceleration in the y. Well, the first thing we want to do is we want to show what we know we're doing. And we know that this thing's not accelerating. It's a traffic light. It's just hanging there. It's at rest. And so it looks like the sum of the forces in the x direction equals 0. Sum of the forces in the y direction equals 0. Now, we might not solve both of these. We'll only do it if we have to. Let's take a look at what happens in the x direction first and see if we can go from there. I think we're going to have to solve both of them. But anyways, in the x direction, we have the x component of the tension force. So we have a tension 2 in the x. That's positive, because that's the positive direction. And in the negative direction, we have the tension in 1 in x and equals 0. I want you to do this. I want you to stay organized like this. This equals sign, I want you to carry it down. This is the 0 side of the equation. This is the sum side of the equation. And we're going to keep it that way until we have to mix it up. What I don't want you to do is just say sum of the forces equals, and then sum of the forces here, and then keep sum of the forces, and then later maybe you say it equals 0. No, don't do that. Sum of the forces equals 0. put the sum here. Leave the equal sign right there, and this side will be my 0 side, or mass times acceleration if this was accelerating, but it's not. All right, T2x, what is that? That is, it's T2, and in the x direction, it looks like it's a cosine of 60 degrees minus T1 cosine of 30 degrees equals 0. All right. Okay, so I have one equation with two unknowns. I need more information. I'm going to get that from the y side. So let's see what we got in the y.
Pause the video now.
In the y we have, notice T1. Y is positive plus T2. Y minus the weight equals 0. We have two upward forces. We have one downward force. We have three forces, 1, 2, 3 in the y direction, equals 0. Notice both of these are positive because they're up, and the weight of the object is down. All right. So T1y is T1 times the sine of 30 degrees plus T2, which is sine of 60 degrees, minus, I'm going to replace FG with MG, equals 0. So FG is MG, because they gave us the mass, so we're going to be using MG. All right. Two equations, two unknowns. Well, we can deal with that, I think. So let's deal with that. Let's not just sit here and talk about it. Let's actually do it.
Pause the video now.
All right, let's see. I think I will solve this for T2, plug it in there. There's many ways to do this. This works out kind of nicely. I'm going to solve this for T2 equals T1 cosine of 30 degrees divided by cosine of 60 degrees. All right, let's take all this mess right here and put it in for T2. We'll put it in there. And then we'll solve for, we'll be able to get T1 out of that. All right, so we got T1 sine of 30 degrees plus T2, which is this, T1 cosine 30 degrees divided by cosine of 60 degrees times the sine of 60 degrees equals, I'm going to take mg to the other side, equals mg. All right, well, I'm certainly getting excited now because I see I have sine over cosine, sine of 60, cosine of 60, that's tangent. I can factor out the T1. T1 sine of 30 degrees plus cosine 30 degrees tangent of 60 degrees equals mg. All right, T1. Therefore, equals mg divided by sine of 30 degrees plus cosine 30 degrees tangent of 60 degrees equals, and then I can put in what mg is. I'm going to put those in right now. I'm going to erase that. I'm going to say m is 5 kilograms. 5 kilograms times 9.8 newtons per kilogram. I have 24.5 newtons. T1 is 24.5 newtons. Let's take T1 and put it into there, and we'll get T2. 42.4 newtons, T2. That's what I get. Let's see. Now, without looking at the picture, if I'm looking at that and looking at that, this rope better be more vertical because it seems to be holding more weight, and the more vertical rope will hold more weight. Let's see if it is. If it's not, we got a problem. If I haven't done this demo in class, we'll do it in class. I'm not going to do it right now because I don't really have stuff to do that. Let's see, we got T2 is this one. It's at 60 degrees, although that doesn't look like 60 degrees, but believe me, it is. 60 degrees, it's more vertical, it is holding more weight. All right, well, that's good. It doesn't mean it's right, but it seems reasonable. I'm going with it. Let's see if that agrees with you. I could have made a mistake. I don't know, make them all the time. But anyways, that seems reasonable. The process certainly is solid. Maybe there's a calculation issue. But really what you need to do is set up what's going on in the X, keep that over here, Y here, keep things organized, separated, because we're going to end up with, here we have 2 columns, but once we get into the third law, we're going to be dealing with like 8 columns. All kinds of interactions going on, and we need to stay organized, otherwise it really turns into a jumbled mess. All right, let's try another one. That was fun. All right, here we have a block on an inclined plane. Like that, a 50 kilogram block on an inclined plane at 30 degrees. I got circle the object of interest. Like that. And I'm going to tilt my axes. If you ever have an acceleration, you want it to be along one axis. And this thing is going to accelerate. It's going to accelerate down the x-axis. This is moving at constant velocity. But we also want our velocities to be along one axis, so we don't have to break it into components. All right, what do we have? We have the normal force. I see we have nothing in contact except for the surface. The surface is always going to have a normal component, a perpendicular component, and since it's sliding down the ramp, it's going to have friction this way, and it's sliding, so it's going to be kinetic friction that way. Those are the only contact forces. And we're also going to have, probably should have used different colors, but that's okay. We have the force of gravity like that. Voila, different colors. All right. All right, one of the keys on these problems, and in case you're having problems seeing that, is this is a 30-degree angle. This is the ramp. And you need to have that animation right there, blink.
Frogs with dirty little lips, dirty little warts on their fingertips, dirty and green, tiny and mean, flopping around by the edge of the stream.
Yeah, right there. We can see that the angle with that the ramp makes with the horizontal is also going to be the angle that the negative y-axis makes. And I like to do that thought experiment. Think about if the ramp goes down like that, which angle here goes down? Well, if this goes down like that, then the force of gravity and this start lining up. This also goes to 0 as that goes to 0. You want to try and picture that. This is Newton's second law, but of course in this case it's a constant velocity, so the sum of the forces are going to equal 0. But that means that the sum of the forces in the x direction equals 0. Sum of the forces in the y equals 0. If you want to start off with the general expression of Newton's second law and say equals mass times acceleration initially, that's fine. But then immediately show that you know that there is no acceleration, it's 0. If you keep carrying mass times acceleration through, that's showing that you don't know what's going on. Don't do that. Don't do that. All right, so they want to know what is the normal force and what is the force of friction. What is the normal force and what is the force of friction? That's the question. All right, well, let's take a look.
Pause the video now.
Well, friction's in the x-axis, so we're going to have to solve that. And normal is in the y. We're going to have to solve that. I'll just start off with x. In the x direction, we have a positive friction force. Positive because it's to the right. Force of friction, kinetic, is that way. And then we have a component of gravity, which is Fg sine of 30 degrees equals 0. So we have friction that way and a component of gravity that way. All right. So it looks like that the force of friction is going to be mg sine of 30 degrees. I'm going to use mg because they gave us the mass. All right. So let's see what we got over here. In the y direction, we have the normal force up. Normal force is positive. And negative, we have minus Fg cosine of theta equals 0. I guess only two forces there. So then the normal force equals mg cosine of theta. 30 degrees, actually. We'll leave it as theta. I better not write theta. We never said it was theta. We never said it was theta. Let's change it to 30. All right. There we go. Then we plug our numbers in. That was easy. 5K, 9.8 newtons per kilogram. Sine of 30 degrees. Normal force equals 5 kilograms. 9.8 newtons per kilogram times the cosine of 30 degrees. All right, I got 24.5 newton. 42.4 newtons. All right. All right, the key is make sure you have a solid diagram. Circle the object of interest. Make sure you're taking into account all the forces that you need. Get a solid free body diagram. If that's not right, everything else is wrong. So make sure you have that. Make sure that you've taken the time to say, okay, I have contact. A surface can apply two forces, normal and maybe friction. In this case, there is friction. And then the force of the distance, which is gravity. Then state the physics. Break your vector situation into a scalar situation along the x and y axis. And solve away. Relying on your free body diagram to make sure you have all the forces. All right. That's a good start to Newton's second law. Have a good weekend, and I'll see you in a few days. Bye-bye.
Extreme physics.